Hi everyone, welcome to this supplementary video. In this video, we will learn about an alternative derivation of pressure-driven flows. There was a very nice question asked in morning in the lecture about what if we change the coordinate system and so on. And so I wanted to kind of go through the derivation again and show how the two methods are consistent and how they have to be consistent with each other. So we will do that. I will derive flow rates from two different approaches and then an average velocity from two different approaches and show how they're both exactly the same. Okay, so that's the idea. And this will again be good practice for you for the exam and for also for your homework problem on pipe flows and so on. So, okay, so the problem we focused on in morning in was, the that there is an x and a y, and that it is 2h distance between the two. And we said there is pressure P1, a pressure P2, and we found the answers. We found the velocity profile to be u of y is equal to minus delta P by L h square by 2 mu into 1 minus h by h whole square. Okay, so this is what we found in the morning. Remember that delta P is actually P2 minus P1. And we made some assumptions here. I just want to recall them: steady, unidirectional, and no gravity. Okay, no gravity. So these were the assumptions we made in the system. Now, how did we arrive at this point? We said continuity gave us del u by del x is equal to 0, which implied that u is only a function of y. And Navier-Stokes in the x direction. In the x direction Navier-Stokes, we found del p by del x is equal to mu del square u by del y square. And in the y direction, we found del p by del y to be 0. And then this implied that it is dp by dx is equal to mu d square v by dy square, because u is only a function of y. And this implied that p is only a function of x. And this means they have to be constant because this is a function of x only, function of x, and this is a function of y only. And we said this is mu d square u by dy square. And then we said u of minus h is equal to 0, u of plus h is equal to 0. And both of them are combined. Once you integrate, you get to this point. Okay, so this is just a quick reminder of how we came about the result of u of y. Okay, now my parallel coordinate system, which I can also do, is I can say my x and y actually start from here. Okay, so that in this case it was y equal to small h and y equal to minus h. But here I have y equal to 0 and y equal to 2h, and I'll call them y prime. Okay, just so that there is no confusion. There is y prime. This is just a new coordinate system I've defined where I've moved the y to y prime, and it goes from 0 to 2h. So what will happen in this case? Okay, so, and again I have p1 and p2. So the question is, what will the velocity profile look like, and will they be same as the one on the left? Okay, so that's the question. I do want to emphasize one thing. We can more formally do this, but I think it should be pretty obvious that we don't really put anything in this equation where it matters, the coordinate system matters, until we write the boundary conditions, right? So in other words, what I'm saying is, here if I do continuity, I will basically conclude that del u by del x is equal to 0. So I will conclude use a function of y prime, and same as just the same as the other equation. If I do Navier-Stokes in the x direction, I will say dp by dx is equal to mu d square u by dy prime square, because y was on del p by del y prime equal to 0. And then this will become delta p by L. Okay, so this essentially is the same approach. The only thing is the boundary conditions are now different. The equation is the same. It's just y prime, y replaced by y prime. But my boundary conditions are now u prime of 0 is equal to 0 and u prime of 2h is equal to 0. Okay, so that's the difference, right? Everything else remains the same because I'm not really applying any domain knowledge anywhere, like the boundaries anywhere other than just at the end. Okay, sorry, apologies. This is not u of u prime, u of y prime equal to 0. That is what I meant. So now let's do this more in detail. So the left hand side is delta p by L is equal to mu d square u by dy square, u of minus h is equal to u of plus h to 0. Here I have delta p by L mu d square u by dy prime square, where u of 0 is equal to u of 2h to 0. Okay, so this is essentially my whole difference between the two cases. In one case I have in terms of y, in one case I have in terms of y prime. Okay, so I will skip some steps here which are not difficult. We did this in class. So I will just write u of y, integrate twice. So I will get delta p by L 1 by mu into y square by 2 plus c1y plus c2. Okay, so this is what my integration will bring, and by the same logic here I will get integrate twice. I will get u of y prime is equal to delta p by L into y prime square by 2 into 1 by mu of c1 y prime. Let's not call it c1, let's call it b1, just some constant b1 y prime plus b2, which is what I'll get. Okay, so this is my just integrating this, and we did this in class, so it's the same thing. And you can please do try this, and if there is confusion, do feel free to ask us. Now I'll apply the boundary conditions on one of them, to both of them side by side. So hopefully you can see how to go about this. So if I do u of capital H, it is delta p by mu L into h square by 2 plus c1h plus c2 equal to 0, right? That is my one boundary condition. And this is u of minus h is equal to delta p by L, delta p by mu L. Y square is minus h square, so it's still h square by 2 minus c1h, because y is minus h, plus c2 is equal to 0. Okay, so I can clearly see that if I add them, I can just simply get the value of c2. And if I subtract them, I can get the value of c1. So if I add them, so I can cancel out c1, then I'll get c2 is equal to minus delta p by mu L into h square by 2. And when I subtract them, I simply get c1 is equal to 0. I believe that is correct. So this is what we get. So from here, I get u of y is equal to delta p by L, y square by 2 mu minus delta p by, because c1 is 0, delta p by L 1 by 2 mu into h square. And sorry, there I apologize. I think I started making I do that sometimes with small h and capital H. So just for simplicity, I'll just change this capital H here everywhere because I carried over the two capital H just to show you where I have it is 2 capital H square here. I do this mistake a lot, so apologies, but hopefully this is not too confusing because all I'm doing is this replacing the same variable as capital H everywhere. Hopefully this should be correct. I'll just give a one look to make sure. Yes, so okay, so it's just replacing small h by capital H throughout, and you do get the answers. Yes, everywhere else I have it correct, and so I get here capital H square. Okay, and so when I take it out, and I just write minus delta p by L h square by 2 mu, and I can say 1 minus y by h whole square. Okay, so this is the u of y that you have seen in class, just with the small h replaced with capital H. Okay. All right, so this is the equation. Now I need to do the other side of it, which is u of y prime. So I will go u of 0. So u of 0 is equal to 0 plus 0 plus b2. And so that is equal to 0. So this means implies b2 is equal to 0. Okay. And now u of 2h is delta p by L 1 by mu 2h whole square by 2 plus b1 into 2h equal to 0. So this implies that b1 is equal to minus delta p by L mu L into h. I believe this is what you get. Let me just make sure I verify this. Yeah, that's what you get as minus delta p by mu L h. And so that's our b1. So now u of y prime is delta p by L 1 by mu y square by 2 minus delta p by mu L into h times y, right? So that is what I'm seeing here. So we will see if I made a mistake or this is correct. So let's keep going. So u of y prime, we take out minus delta p by into mu L h square by 2, or I just prefer to write it as h square by 2 mu. Then I get 2y by h minus, sorry, this is y prime, not y. 2y prime by h minus y prime square by h square. Okay. So this is what I get as my answer. Okay. So just to reiterate, I have written everything in terms of y prime by finding b1 and b2. b2 was 0. And b1 came out to be minus delta p by mu L h. And then I have taken this h square minus delta p by h square by 2 mu out. Why did I take that out? Because I want to compare it with this expression here. This is the part. And so then the part inside is y prime 2y prime by h minus y prime square by h square. So here, how do I show that they're both the same? So what I will do is I will try to express this in terms of the one that is written on the left hand side. So I'll say 1, I will add 1 and I'll subtract 1. So I will say 1 minus y prime 2y prime by h square 2y prime by h minus y prime square by h square minus 1. Okay, so just added 1 and subtracted 1. And if I do this, minus delta p by L into h square by 2 mu. This becomes 1 plus 2y prime minus y prime square minus h square by h square. Okay. And this becomes minus delta p by L h square by 2 mu. I hope some of you can see this second term here. This is 1 minus y prime minus h whole square by h square. Okay. So it's y prime square plus h square minus 2y prime times h. By the way, I forgot an h here. Y prime minus h whole square. Okay. So now this, we know that if I look at this coordinate system here, I can convince myself that y prime minus h is equal to y. Right. So I'm moving the axis just literally by the distance h, which I have done here, and I've gotten the same answer essentially, right? So it's 2y prime by h minus y prime square by h square. And so it's the same answer. I've just moved the axes and I get to the same point. So essentially, it does not matter what coordinate frame you choose. Ultimately, the solutions have to be equivalent and exactly going to sort of, if you plot them on an absolute scale, they have to be the same. It's just your coordinate choice. Okay. So now let's also do a calculation of flow rate. To calculate flow rate, we know Q is equal to W times, and remember, width was the distance into the plane. So this was W, right? So this was W, the width into the plane. So W times 0 to minus h to h minus delta p by L h square by 2 mu into 1 minus y by h whole square. And then that becomes minus delta p by L into h square W by 2 mu into y minus y cube by 3h minus h to h. You just have to put the limits. Y cube by 3h square. So what you get out is, and minus h by h in capital, apologies, this is just habit, capital H plus h. Okay, so this, and then so when you do this, you get out 2 minus 2 by 3, so 4 by 3. So total is 2 by 3. So it's minus 2 delta p h cube W by mu L as my flow rate. Okay, so this is what I get, 2 by 3. Okay. 2 by 3. This is my flow rate. And I can do the same calculation, but now going from 0 to 2h, but with y prime. So minus delta p, there's a dy here, minus delta p by L, h square by 2 mu into y prime by h. So it was 2y prime by h minus y prime square by h square dy prime. And if you do that, basically what you will find is minus delta p by L h square W by 2 mu. So you get here 2 by h into, sorry, 1 by h y prime square minus y cube by 3 h square 0 to 2h. And so here you will get 4 minus 8 by 3. So minus delta p by L into h cube W by 2 mu into 4 minus 8 by 3, which is equal to 4 by 3, and which cancels out. So we do get it correct. By 3 mu. Okay, so we do get 4 by 3 times half, it's 2 by 3. So minus 2 delta P H cube W by 3 mu L. So finally, you can see from both the calculations, even the flow rate matches, which it has to match. Otherwise, we are making a mistake somewhere. So here the limits are 0 to 2h. Here the limits were minus h to h, but we do match the solution, and it nicely comes out to be the same. Okay, so I might have rushed a little bit of integration, but and some of the math tests, but the procedure hopefully is clear. I highly recommend practicing these kinds of things on your own and making sure you're comfortable with all of these things. And I think that kind of just helps you gain better experience of different flow calculations. All right. With that, I will end this video and I look forward to seeing you in the next lecture.